what can we do with this? Different than previous problems where it was something like 3/8 or 5/7. Here I have some variable u over 7. All right, well, I'm just going to attack it in a similar way. An inverse trig function is an angle. So this says the cosine of what angle is u over 7. And then because the arc cosine is that angle, the problem I want to answer, once I figure that out, is what is the tangent of that same angle? So let's draw a triangle. Now, since I don't know what u is, the scale of the triangle doesn't really matter much because u is some variable. Let's say this is my triangle there. Right angle. Let's let theta be that one right there. So on a right triangle, cosine is the adjacent length, adjacent to the angle, right, next to, divided by the hypotenuse. So we're saying the adjacent length is just called u, hypotenuse is 7, and then we have our missing side right there, I'm going to call question mark, which is our opposite side, right, opposite across from the angle. Tangent on that same triangle, right, theta is going to be the opposite side divided by the adjacent side. So now I just got to figure out what the opposite side is, and I got it. Pythagorean theorem says the adjacent side squared plus the opposite side squared is the hypotenuse squared. And I need to solve for question mark, right, which is my opposite side. So question mark squared equals 49 minus u squared. And then we take the square root of that. And you might be tempted to cancel some squares with square roots, but I want to caution you against that. So simple example, suppose we had the square root of 5 squared minus 3 squared. Now, order of operations to do this, we would take 5 squared as 25 and 3 squared is 9, right? We got to do what's inside because the square root is essentially a fancy parentheses with an extra step. 25 minus 9 is 16, square root of 16 is 4. That is the correct answer according to the order of operations. If we tried to cheat this and cancel squares and square roots there, then we'd be tempted to say that this answer should be 5 minus 3. 5 minus 3 is 2, and 2 is not the answer. So this was bad math. Don't do that. Order of operations, the subtraction, what's inside the parentheses has to happen first before you can deal with the square root. That's the last step. There's no shortcut. So this doesn't simplify anymore. That's it. That's as simple as it gets. Now you might say, well, I could factor that. You could, right? 49 is a perfect square. U squared is a perfect square. That would factor as 7 minus u times 7 plus u. But is that really, and that's all inside the square root, is that any simpler than what I have above? I think that took more ink, so I think that's not simpler. So I am convinced that this is the simplest version of the opposite side, given u for the adjacent and 7 for the hypotenuse. So coming back to my problem, I want to know what the tangent of that angle is, and the tangent of that angle is the opposite side, square root of 49 minus u squared, divided by the adjacent side, u. And since the top does not simplify in any way, I really can't clean this up anymore. That's it. That's what I got. And unfortunately, we can't easily check this on a calculator, but we can kind of sneakily check it. So u is a variable. So that means when I use u in an expression like this, I can think of this as a function. So maybe this original red thing here, I can think of this as some function of u. But now I have this new version of this function of u that doesn't include tangents and arc cosines. So we could graph the red function using an x instead of a u, and graph the green function using an x instead of a u, and see if they look like the same function. Let's give it a try. All right, so original one then would be y equals the tangent of the arc cosine of u over 7. So I get this funky curve here. Zoom out on it a little bit. It's cute. And now my claim is that should be the same function as the square root of 49 minus x squared. Oh, it took u. I typed u instead of x, and it treated it as x. That's cute. What a shock. I'm going to put an x there just to be safe. All right, same thing. All right, square root of 49 minus x squared. Ooh, semicircle. And then what happens if I divide that by x? What I should see is that the purple, let's turn it off, and the green sit right on top of each other. Okay, if I'm not sure about that, I could use function notation to double check. Let's call this f of x. And let's call this one down here g of x. And I could just pick some x value in this range, like that's 0 and that's 10. 5 is in this range. So I could say, what is f of 5? 0.97979, blah, blah, blah. What is g of 5? Better be the same thing. And I get the same number. So the graphs look the same. I picked some x value, and the x values are the same for that x value. So I'm getting more confident that, yeah, I did this correct. So that problem was a little wilder than others we've done, because instead of an actual number, like an angle to start with or some ratio, I had a variable involved in there. And so after I evaluated both the cosine inverse with the tangent, I was still stuck with a variable. And that is not uncommon in trigonometry. So it turns out there are some combinations of trig functions and inverse trig functions that end up being related to some rational functions and square roots because of the Pythagorean theorem and the relationship on right triangles of these things.